Back in the year 2004, that was 20 years ago, I took some solid lead chloride and some distilled water, and I put them both in this bottle. And the lead chloride, since then, has not been able to fully dissolve 20 years later. Now, I want to say that some of it has dissolved a little bit. Even things that are insoluble actually dissolve to a really tiny extent. And at any given time, a few of these ions are dissolving, and a few of them are undissolving, setting up a little equilibrium. And this is an example of a heterogeneous equilibrium in which you have substances that are in different states from each other. They might be solids, liquids, gases, or aqueous ions like these over here. And this video is all about heterogeneous equilibria and how we deal with them. So hello everyone, and welcome to this video on heterogeneous equilibria. This is part 2 of our series in chemical equilibrium, and just some detailed things we have to deal with. I have another example of a heterogeneous equilibrium. These are vials of bromine, the element bromine, and you can see hopefully that there's a little bit of liquid at the bottom, and then there's some bromine, this brown vapor up here. And not all the liquid has evaporated. We're kind of in equilibrium. They're doing some evaporating, but they're also unevaporating at the same rate, but just into a different phase. So I've got some samples here, and they have slightly different amounts of liquid in it, but I'm hoping that maybe in this little crude test, you can see that the color of the vapor is very similar. Like I'm getting a similar amount of vapor in there, regardless of how much liquid is here at the bottom. And I think that's kind of an important concept for today's video. So heterogeneous equilibria are ones that contain substances in more than one state, such as solids, liquids, gases, and solutions. We'll get that definition out there. And I wanted to talk about the bromine first. Here's the equilibrium where bromine is evaporating into bromine gas. And that actually increases at higher temperatures because more molecules have enough energy to break free. And this is a graph of the vapor pressure of bromine above the liquid that it's in. And it is an equilibrium, dynamic equilibrium where things are evaporating and unevaporating at the same rate. So because it's an equilibrium, we can write an equilibrium constant expression for that. So we would have the product, bromine gas, over the reactant, bromine liquid, although this is not a reaction, this is more of a physical process. But here's the big important point for today. We're going to simplify this into just the bromine gas. And here's why. Because solids and liquids have a constant concentration, and these brackets mean concentration. That concentration is pretty much constant. And so it sort of can get wrapped into the equilibrium constant, and we can ignore it. And we should only include substances that are in the gas phase or the aqueous phase because their concentrations may actually change. So that's the big idea for today. Omit anything that is a solid or a pure liquid. So back to my lead chloride. I could write a little dissociation equation for the dissolving of lead chloride. It does happen a little bit, not a lot, even though it's insoluble. And if I wanted to write the K expression for this, I would have my products, lead, 2 plus, need a better pen, and chlorine, and there's a 2 in front of it. And so I put that, but because this is a solid and it would normally be on the bottom, I'm going to omit it. I'm going to keep it off because its constant concentration gets wrapped into the equilibrium constant. And this is actually a special kind of equilibrium constant called a solubility product constant. We'll get to those more in a few videos. You might see this KSP, and that just stands for solubility product. Things dissolving, but then undissolving in equilibrium with each other at the same rate. So that's a nice equilibrium expression. So again, leaving out these solids. I'll do one, and then I'll have a pause the video moment. This is a very typical kind of question you're going to run into. And I've got the equation here, and it says write the equilibrium constant expression for this reaction. I'm not going to do any calculations in this video. I'm just going to talk about how to treat heterogeneous equilibria. So the K is going to be, first thing I always do is I check for solids, liquids in these. I check the states. Okay, and I've got gas, gas, solid, gas. I'm going to not include that one. So my equilibrium constant is going to have the water up top. And then I'm going to have these two at the bottom. So NH3 squared, because there's a 2 there, and the CO2 at the bottom. So we'll call this Kc or Keq. And again, just leave out the solids and or the liquids. All right, let's do a pause the video moment. Here's an equilibrium set up between iron and water. And take a moment, pause the video, see if you can write the equilibrium constant expression for this. Okay. So here we are with the answer that I got. I omitted this iron oxide compound and the iron, but I included the gaseous hydrogen to the fourth and the water to the fourth. That's a cool looking equilibrium constant expression. I like that a lot, so I put a heart next to it. Okay, and the last thing I want to do as a public service to you, the faithful viewers, and maybe AP chemists, is I want to warn you about a type of problem that my students hit this week, and you might hit it sometime. It's a very popular type of problem where they won't tell you right off the bat that it's heterogeneous, and so you're left scratching your head and wondering what's going on. So here we have the equilibrium: calcium carbonate decomposing into calcium oxide and carbon dioxide. And it says for the system above, Kp was 3 at some temperature. Which of the following are at equilibrium? For those that are not at equilibrium, which direction will the system shift to reach equilibrium? Okay, so they give you these masses and then the things, and so you're probably left thinking, okay, so we got a lot of things to do here. We have the calcium oxide, we have the carbon dioxide, which is now in a pressure situation, and the calcium carbonate would go on the bottom. And a lot of people would get to this point and start, fighting back the tears because what are we supposed to do with this mass? How do I change it into moles and molarity? And what do I do with everything else? And the answer to this is that there is too much information here that you do not need. Because if you note to yourself that it's heterogeneous, these actually go away, and the K is simply equal or proportional to the amount of CO2 that's present. And you could do it as a Kc or a Kp, pressure of CO2. Okay, and we'll put that in parentheses. Notice the diagram over here. So there's varying amounts of the solids down here. This is a very popular diagram. You'll probably see millions of versions of these. But if you count the number of CO2s up here, it's the same in both cases, even though the amounts of solids have changed. So really, the amounts of solids have nothing to do with the shifting of the equilibrium. As long as there's some of each there, we can basically ignore it. So it's all there and it begs to be worked with, but don't do it. You don't actually need to. So all you really need to do is say to yourself, oh, what's the current pressure of CO2? What if it's 1.23 atmospheres? Well, Kp says it's supposed to be 3, and that's less than 3. And so when we do our reaction quotient, we say to ourselves, oh, right now it's got less pressure than it should, so the equilibrium is going to shift to the right to produce more CO2, and that will increase the amount of calcium oxide present and decrease the amount of calcium carbonate present. If the pressure of the CO2 in this container is actually 3, then we are at equilibrium. And so 3 would be the Kp, and that's what we're told that it is. So great, it's at equilibrium. If the pressure of CO2 somehow got too high, and therefore the Q value, the current pressure, is higher than 3, it will shift back to the left to decrease the amount of CO2 that's present, in a nice example of Le Chatelier's principle. So there you go, a quick friendly warning about this type of problem, which if you hang around in the chem lab long enough, you're going to see it. So hopefully that will help you to not get tricked in chemistry class. Well, that's it for today on heterogeneous equilibrium. If you have a question that you'd like me to answer or solve, feel free to send it to me or put it in the comments. In the meantime, happy solving and have a great day.